Hello, everybody. Today, my name's Steve Jones. Today, Jane Owen is going to go through radiation and stars with you and give you an introduction to uncertainties.
Hello, everybody. This is our last session of the catch-up sessions. I hope you've enjoyed them and I hope you're getting something out of them. Okay, so what we're going to do today is radiation of stars, and then we're going to hopefully go on to an introduction to the uncertainties. Now, this is what you did last session with Steve Jones with the photoelectric effect, and you went on to absorption and emission line spectrum. And in radiation of stars, when we've got a distant star and that passes through an interstellar kind of medium around that star, then we can we don't usually use a prism, we usually use a spectroscope here on Earth to split the continuous, the white light into a continuous spectrum. And what we get are the black lines on a rainbow background. And this is the one that we are interested in, because this gives us information about what elements are actually from the interstellar kind of tenuous atmosphere around the star that we're receiving the white light from. And these black lines give us a fingerprint. It gives us details about the chemical composition. So we haven't had to go anywhere to get that information by just analysing the white light. Now, what we do though is we take it a stage further, and we take that light and we plot it. And what we plot is the intensity I, so intensity, which is given by the power per unit wavelength per unit area. Okay, and that would be in watts per meter squared. And you've got all the different wavelengths along here, and these wavelengths could be in meters, all right, and very often it's in nanometers. So you could have it in meters, or you could have it in nanometers, which would be, we can say nanometers there, which means it's times 10 to the minus 9 meters. Or sometimes you might see it in angstroms, which means it will be times 10 to the minus 10 meters, but it will be a unit of wavelength along the bottom. Okay. And what you'll get is when you take the continuous spectrum, and the continuous spectrum is not just the visible spectrum, but all of the wavelengths received on Earth from that star, and we get something that looks like this. We start off with zero gradient and we go up very, very steeply, zero gradient at the top, and then we kind of like gently kind of like peter out in terms of the amount of wavelength, and this will approach zero, okay, down here, and this here will be having a gradient up here of zero, i.e. flat, and here will be gradient equals zero. So this would be the spectrum of radiation received by the star. We call that the black body because it's a perfect emitter. It's emitting all wavelengths. Okay, so we've got a steep initial gradient and then we've got a shallower gradient. And there are two laws that go with this and give us a lot of information about the star. Okay, now the first one is what we call Wien's displacement law, and that will give us and lead to us the temperature of the star from knowing the peak wavelength. So wherever the peak is, go down to find that maximum wavelength or lambda peak, And then from that, we can use the peak wavelength to give us the temperature. So we can write the Wien's displacement law as lambda max or peak equals W over T, where the T is the temperature in Kelvin, okay, and W is Wien's constant, okay, and Wien's constant is given to you on the front of the data booklet, so you don't need to remember it, but I'll put it in here now, 2.90 times 10 to the minus 3 meter Kelvin. Okay, all right, so that's one. So if we know the maximum wavelength from the graph that we're given, we know W, so we can rearrange that equation to work out the temperature of the star. The second equation that you will need is Stefans Law. And Stefans Law will track back to work out the size of the star, and we can get that from looking at the intensity and how much is received here on Earth. So we can write Stefans Law as power equals area A times Stefan's constant sigma times T to the power of 4. Okay, where A here is the surface area of the star. Sigma is Stefan's constant, and T is the temperature that we've worked out in Wien's displacement law. And Stefan's constant again is given to us in the data booklet, so we can put that down, 5.67 times 10 to the minus 8 watts per square meter Kelvin to the minus 4. Okay, now it's not as straightforward to apply this, and this has to be applied with due care, because we have to work out first of all the power. All right, and if we've got here on the graph, we've got the intensity, so the intensity is equal to the power per square area. All right, and if we times the intensity with the area that the light spreads out over, here to here on Earth from the star, we get the power of the star. So this is the power of the star in the law, and to get the power of that star, we have to kind of imagine that if this is the star here, and then I blow it up, then that light is spreading out over that entire surface area. So what we get here on Earth, we only get a tiny little fraction of the whole power that is spread out from that star. So we are getting the intensity, the power per unit area. So what we want to be doing is we want to kind of calculate how far the star is away, and from that the surface area that light spreads out over. And once we've got that, we can work out the power of the star that we can put into the equation for Stefan's law. So the intensity comes from the graph. That part comes from the graph. That's the intensity. This area here, though, is the surface area. The star's radiation spreads out over, and it's given by the surface area of like a sphere, and that's given by 4 pi r squared, where the 4 pi r squared, I just want to check that I am right, 4 pi r squared, that r there is the distance the star is from Earth. So you can see that there's going to be a little bit of a confusion here, because this surface area here will be different to the surface area that is actually in Stefans Law, because this is the surface area of the star, still given by 4 pi r squared, where r is the radius of the star, not the distance from the star to Earth. So can you see, you know, kind of like the difference and how we've got to handle this and be very, very careful? Because you've got to remember that the graph that is shown to us over here of intensity against wavelength is just a fraction of the power from the star, and we have to track back then to get the total power of the star, and then we can use Stefans Law, and then we can get that will substitute into here, and we can then manipulate this equation to give us the surface area and then ultimately the size of the star. Okay, right, I'll come back to that, okay, and give you a little bit of time to take that in, and hopefully I'll show it a little bit more clearly. Now, this is an example of intensity against wavelength for a distant star. This is the trace that we've got. So we're starting off 0 here, it goes up steeply, 0 gradient at the top, and it goes off gently. What I've done is I've taken the visible spectrum, which ranges from about 400, 450, some books say 450 to 800, some books say 400 to 750, but I've taken the spectrum, all right, and placed it on top of the graph. You almost have to do it mentally, kind of like put it on top. So say to yourself, say 450 to 800, and you place it on top, and then you have to judge yourself how much of the radiation is attributable to the colours and the intensity of those colours. So you can see with this particular wavelength, distribution of wavelength, there's a roughly equal amounts of blue, green, yellow and red. So we can say that there are roughly equal, you know, they doesn't have to be exactly the same, but you've got a bit of all radiations in the visible spectrum, and therefore we can say it's a white star. And stars have different characterizations depending on where the visible spectrum lies. So for example, if I had a star that goes like this and it just goes like that, okay, let's just say, then there will be a high proportion at the blue end and very little at the red end. So we could probably get away with saying that that was a blue star, okay? So you can see here that actually the colour tracks back of the star, that they characterize that star, tracks back to the temperature of that star. So here I've got 3 different temperatures. We've placed our visible spectrum over, and we can come out with different characterizations for those stars. So for example, that last one there at the 4000, there is a lot of red compared to any of the blue there. I know there's not a lot of anything, but you can say probably that it's a red star, or yeah, okay. So this is how we categorize. Now you don't need to know at WJC exactly how to categorize them, and you don't need to know the spectral type, and you certainly don't need to know all the different colors, but I think it's probably good to say that if the majority is in the of the visible, all right, is the only blue, you can say it's the blue end, and therefore it's a very hot star. Whereas if you're looking at this lower one here, then the majority of the radiation is in the red, so therefore we can say it's a red star. And if there's an even distribution of all of them, like this middle one, you can say that it is a white star because it's got equal distribution of all of the radiation. This one, this highest one here, you could go with a blue-white star, okay, because there is a high proportion of blue compared to the others, but there is a bit of all of the other colors as well, so maybe a blue-white star. Notice that this wavelength here is in angstroms, something slightly different. Okay, so right, I just want to see. So isn't that interesting? Because what we've got from that spectrum there, we have two bits of information that we can get. We can get the temperature and we can get the size of the star, because we can get the intensity, track back to the power, and then we can substitute it to find the size of the star. And we can do this so we can get the chemical composition, we can get the size, and we can get the temperature, all by sitting here on Earth and analysing through a spectroscope, which is just a small metal object, what we are receiving from those distant stars. So we haven't had to go anywhere. All we've had to do is interpret that spectrum. Now, you did a little bit of this with Mr. Jones, Steve Jones, last lesson, the photoelectric effect. Those lines, those emission lines, relate to specific energy jumps within the shells of the electron configuration around the elements, around the star. So you have to take energy in order to jump an electron, say from energy state 2 into energy state 3, and the atom does that by stealing or taking a photon of energy from the visible light spectrum. And that's why we see the black line, because what happens eventually is that excited electron will relax back down to the lower level, but it will re-radiate it in a different direction, and that direction won't be towards Earth, where the rest of the visible light is passing from the star to us. Okay, and if we have those energy transitions all from energy level 2, then that will be Balmer series. And here we have hydrogen's Balmer series, where each of those black lines relates to an energy jump from 2 to another level. And you will have to be able to take the energy difference, so whatever the difference is between these energy levels, so E3 minus E2, and then take that energy difference. You'll often see these as negative numbers, okay, and because you have to put energy in order to kind of excite them up to a higher energy level, and that will give you Planck's constants times by the frequency, the energy of the photon, and then you can use C equals F lambda to work out what the wavelength is. So frequency equals C over lambda, so equals HC over lambda. So whatever that energy change is can relate to the wavelength of light that has been, say, emitted, all right, been taken from the visible spectrum and leaving a black line. Okay, all right, that might not be specifically that one, but that gives you an idea. And the beauty of hydrogen is that the Balmer series, the black lines are in the visible spectrum. But you've done this with the photoelectric effect, and you can have, you know, look at the last revision session to get more information. Okay, right, so that is everything that you need to know for radiation to investigate stars. I just wanted to make sure that I think what I'm going to do is I'm going to go on to uncertainties, but are there any questions on any of this material so far, Steve?
Nothing at all at the moment.
Okay, all right. I'm just wondering whether it needs clarification a little bit more on this, or shall I move on to uncertainties?
It was clear to me.
It was clear to you. Okay, all right. Okay, all right. Okay. So the learning point really with Stefans Law is that there are two surface areas. There's one surface area where the light spreads out over, and that's dependent on the distance between Earth and the star, and that gives us and tracks back to the power of the star. Whereas the surface area in Stefans Law relates to the surface area of the star, and then that tracks back to the radius of the star. So if you would calculate the power of the star from the intensity on the graph, you will have sigma, which is Stefan's constant. You will have T because that is the temperature at the maximum peak wavelength. Okay, so you can track that back from Wiens. So therefore you're left with the power divided by sigma divided by T4 equals the area, surface area of the star, SA of the star itself, and then you can 4 pi r squared track that back to get the radius. So just manipulate that mathematically, times by 4 pi divide, so power divide by 4 pi sigma T to the 4 equals r squared, and then what you're going to do then is just square root everything, and that will give you the size of the star. All right, now you don't have to do it like that. You can, you know, chunk it and break it up into the different sections of what you can do and lead it from one to the other. You don't have to jump to this final equation at the end here, and that will be the radius of the star. Okay, so I'm going to move on to uncertainties. If there's no more questions, it'll take a little bit of getting used to kind of like putting the visible spectrum on top of whatever you're given. You'll mentally remember, so 450 to 800 nanometers, okay, is the visible spectrum. And you can visibly put that on there and, you know, judge for yourself the distribution of wavelengths. Okay, right, now we're going to go on to uncertainties. Now, uncertainties. Uncertainties is something that we do with any kind of measurements. If we have one measurement, then the uncertainty tends to be, so for example, a meter rule used to measure the length of a book, then our ruler can read to the nearest millimeter, so that we say that the resolution of that ruler is 1 millimeter. We say that the uncertainty, the absolute uncertainty, is 1 millimeter. So if we want to find out the percentage uncertainty, we take the absolute uncertainty and we divide it by whatever reading you get, and then times by 100%. And we get plus or minus 0.34% in this case. And really, we should write this percentage uncertainty or absolute uncertainty to one significant figure. So plus or minus 0.3% will suffice. Now, if the number starts with a 1, for example, if we had 0.1 there, then very often we write to 2 significant figures. Okay, but it's okay to do it to 1 significant figures unless the number starts with a 1 and then we pop in 2 significant figures. Okay, now if we had to repeat readings, let's see, Yeah, it's a little bit different for stopwatches, because stopwatches will read to plus or minus 0.01 of a second. Now, we do not take, so that we say that the resolution of a stopwatch is 0.1 seconds, but that is not the uncertainty or absolute uncertainty, because we've got to consider your reaction error or reaction time. So you can choose any number between 0.1 and 0.6, and I would say, for example, go with plus or minus 0.2 seconds, would therefore be the uncertainty, and we call that the absolute uncertainty. Now, I don't think you can go wrong with that sort of number, not 0.25, that's 0.2 seconds. But that is if you have just one reading. It gets a little bit more complicated if you have repeated readings, and you should argue, really, if you're taking any measurements with a timer, that you should be repeating those readings, because it probably won't be the same every time. Whereas a static length reading, you could argue that actually it probably will be the same each time you measure it, unless you do it in different places. And it's probably good practice there to repeat it. And if it's not the same, I'll show you what we do. Okay, if it does end up being the same, we take the resolution as being the absolute uncertainty. But let's have a series of times. Let's do repeated times now. Okay, repeated readings, and give you an example. All right, so let's say I timed some oscillations and I got 10.4, 10.6, and I got 10.9. Okay, all right, so from that, to get the absolute uncertainty from that, I would have to do half the range. So I get the largest, I get the smallest, I take one away from the other, 10.9, take 10.4 and divide it by 2, because you want to know what you go up and what you go down, and we want the plus minus. Okay, so 0.5 divided by 2, so 0.25, and I would argue there one significant figure, so you're fine to go to 0.3. Now, if you wanted your percentages, so this would be your absolute uncertainty. So the absolute uncertainty in repeated readings is equal to half the range. So you just have to see whether there are repeated readings there, or whether you're expected to take repeated readings. Okay, and then from that, take the absolute uncertainty to get the percentage uncertainty. So you'd have to get the mean. So the mean would be, I haven't got, let's have a look, see what it comes out as. So 10.4 plus 10.6 plus 10.9. Okay, divided by 3, 10.6. So 10.6 equals the mean. I know it goes 10.6333333, but you wouldn't, you'd round it to the same number of significant figures that you've got for the rest. So 10.6 times by 100%, and that would be your percentage uncertainty in repeated readings. So 0.3 divided by 10.6 times by 2.8. So I'm getting 2.8% there. But as with all uncertainties, unless they start with a 1, you can round that to one significant figure. So you've got 3%. All right. Okay, so that would be the percentage uncertainty. That's the only two that you really have to deal with: absolute uncertainty and percentage uncertainty. Okay, repeating readings in time. But it goes with any repeated readings. Now, if you have, for example, up here, the length, and it was 295, and the next one you did was 295, and the next one you did was 295, then you've got 0 range. So you would have to resort back to the resolution of 1 millimeter, okay? And it doesn't matter if you do it plus or minus in centimeters, 0.1 centimeter, as long as you then divide it by 29.5 centimeters, that this is in centimeters and this is in centimeters, before you times it by 100%. So as long as there's consistency in what's above to what's below. Now, I think this, okay, so now we've dealt with single readings, we've dealt with repeated readings, and arguably if you've got to do something at a long length, you should be repeating them top, bottom and middle, to see if it is the same all the way down. Now, what happens if you have a percentage uncertainty in say, a length value and a percentage uncertainty in the width value, and you want to find the percentage uncertainty, say, in the area? What you have to do is, because you're timesing, say the A is the width and say B is the length, so Y is my area, and I've got to times the width by the length. What I do is I get my percentage uncertainty in the width, I get my percentage uncertainty in the length, and I add them up together to get the percentage uncertainty in the area. Okay, so when you're using the width once, you have 1 percentage uncertainty. When you're using the length once, you have 1 percentage uncertainty. And all you're going to do then to get the percentage uncertainty in the area is add the 2 up. Even if you have to divide here and you wanted to work something out and you had a percentage uncertainty for A and B, say, you're using them both once. And even though you're dividing them, you end up adding the percentage uncertainties. You can't add the actual uncertainty because the ratio of that uncertainty to your measurement is very different for the different lengths that you are measuring. So you have to be adding percentage uncertainties, and that's why you have an uncertainty, you've got to almost like convert them into percentage uncertainties, and then you calculate your final value, and then you use your percentage uncertainty in your calculated value by adding up all the different ones that you've been using in the equation, and then you have to turn back and work out what the uncertainty is in that measurement. Okay. So the y equals a squared, a typical one there is cross-sectional area of a circle, area equals pi r squared. So if you've got, we don't usually measure the radius, you usually measure the diameter. So we can say pi d squared over 4. And so we are using the diameter twice. Okay, so pi d times by d over 4. And because you're using the d twice, therefore, whatever the percentage uncertainty is in d, okay, all you have to do is times it by 2, not square it, times it by 2, because you're using percentage uncertainty in one d, percentage uncertainty in the other d, and is effectively they're the same, so you just have to times it by 2. Okay, right, and this is for range of, this is for repeated readings, this next one, which I've gone over, and here is an example. Okay, so let's finish with an example. We've got here length, width and depth. We want to work out the volume. Now, what this candidate has done is correctly worked out the volume. Now, have a look at the significant figures here. There's 3 significance figures here, 2 here, and 2 here. Now, what your answer should be is to the same number of significant figures as the least number of significant figures in the question. So we should be maybe doing it to 140, but you are allowed to go to one more significant figure. So the rule is, look at your number of significant figures given to you in the question, go to the same number of significant figures as those, but if they are different, go to the least, 2 significant figures in this case, but you are allowed to add one more significant figure. So we would be okay to put 137 here, okay? So immediately alarm bells are ringing because that is 5 significant figures and that is not acceptable, all right? Because you can't be any more accurate than what they have given you in the question. Now this candidate here has given the uncertainty correctly as 0.1, that's the absolute uncertainty, but then what they've done is they've times that by 3 because they're using it 3 times, and they don't get their marks here because what they haven't identified is that the percentage uncertainty will be different for each and every one of them. Okay, so this is not going to do it, and there's quite a lot of marks at stake here. So here we are. Another candidate has given another answer here. He's given 4, or she has given 4 significant figures, 137 centimeter cubed. Okay, and correctly, okay, that's 4 significant figures. That's 1 too many, so that's not, that bit's not right. But moving on to the uncertainties, this is right because they've gone 0.1 over 11.5 times by 100, 0.9%, and they've given it to 1 significant figure. Correct. 0.1 over 6.6 times 100, and they've given that to 2 significant figures because the first one starts with a 1. All right, the first number starts with a 1. Correct. And then finally, 0.1 over 1.8 times 100, 6%, 1 significant figure. Correct. So to get the uncertainty, percentage uncertainty in the volume, they have added up all of those percentage uncertainties. And then they have worked out what that is of their answer in real terms. So times it by their uncertainty, percentage uncertainty divided by 100, and they get 11. Okay, now the finishing script here is just a little bit, they won't get their mark because they haven't identified it's good, it's this bit's good, because there's 2 significant figures, because the first number is a 1. So that's great. But it doesn't tie in to finish it off. So 137 centimeter cubed, 3 significant figures, in keeping with what they've given us, plus or minus 111 centimeter cubed. And now that looks tidy because they've got the same, you know, units in the last placing. In effect, you can then refer to decimal placings in the final kind of like representation of that answer, and that will be correct, but this won't be. Okay. Does anybody want anything clarification on anything there? And you can always stop me, and I think we're finished, Steve. Is there anything there?
No, I think it's perfect. Thank you very much, Jane. Very complete, and I hope everybody got a lot out of that. Okay. Thank you all.
Okay, thank you. Bye.
Goodbye, everybody.